Okay. All right, so we're going to take a look in section 8.7 at limits again. And you notice the title says indeterminate forms. We'll talk about what that means. And it says L'Hopital's rule. This is not the hospital. I get all sorts of interesting things. This is L'Hopital. Okay, L'Hopital's rule. And L'Hopital's rule is one that you're going to really like because it makes things really nice, simple. All right, so here's the deal. Recall limits. The basic idea to evaluating limits was being able to change the expression in some way so that you could plug the number in. Okay, that's basically what you tried to do. Maybe you tried to use some algebra, or maybe you tried to simplify something in some way, or maybe the problem already just had the ability to be able to put the number in, and it worked okay. However, there are some forms, when you did this back in Calc 1, that you were not able to find a limit for. Those forms were called indeterminate, and indeterminate forms are the forms where you have 0 over 0, infinity over infinity, or 0 times infinity. Zeros and infinities, those are the issues. Combined in some way.
My high school trick teacher, calculus teacher, on a big tangent one day, that 0 over 0 does not equal 0.
Nope, it does not. It does not. I had an analysis course, which is an advanced topic in a graduate school, mathematics. And our teacher proved both that 0 over 0 equals 0 and 0 over 0 equals 1. So 0 must equal 1. And if that doesn't shatter your mathematical thinking, man, I don't know what would. And he did it using limits. So I want to show you what's going on. Obviously, he didn't actually do that, but he showed the methodology that you can do some of these things that we think we can do with numbers you can't always do. All right, so f and g, if they're functions that are differentiable, what does differentiable mean? You can take the derivative, right? It just means you can take the derivative of it. If it's differentiable on AB, and the point C is somewhere in between those, then as long as the denominator is not 0, except perhaps at the point C, then the limit as x approaches C of the fraction f of x over g of x is the same as the limit of the derivative of f of x over the derivative of g of x, as long as the original function f of x over g of x had an indeterminate form, 0 over 0, infinity over infinity, etc. Okay, so the theorem's almost written backwards of the way you actually do the problem. Okay, the theorem tells you what can happen provided that certain conditions exist, but that means we actually have to make sure the conditions exist before we use the theorem, right? Okay, so let's take a look at an example. We have a limit as x approaches -1. And in order to use L'Hopital's rule, we have to test what would happen if we tried to plug in -1 to all the values of x. So if you plug in -1 on the bottom, what do you get? You do. You get a 0 on bottom. If you plug in -1 on top, what do you get? Nope. You get 0. It's -1 squared minus 2 times -1 minus 3. This is a 1, a 2, and then a -3. So you do get 0. So you have to test that. And in order for you to know, or for me to know that you tested that, you've got to somehow write on there that you got a 0 over 0, and now you're going to use L'Hopital's rule. So I write 0 over 0 somewhere, and then I write an L with a circle around it so that I know what I'm doing next. Okay, I checked that it had the indeterminate form. It did. Because it had the indeterminate form, I'm now able to use this theorem. So the theorem says that I should be able to take the derivative of the top and the derivative of the bottom separately. So this is not the quotient rule, right? I'm not actually taking the derivative of all of this thing. I'm taking two separate derivatives, which is much easier than the quotient rule. What's the derivative of this numerator?
2x minus 2.
2x minus 2. And the derivative of the denominator? 1. And then we try again. We say, okay, let's plug in the number negative 1. So if you plug in the number negative 1 now, what do you get? Negative 4. So the limit is negative 4. What do you think? It's not too bad, right? I'm just taking a couple of simple derivatives and I'm plugging in numbers.
What before, like, to do it, we want to, like, split the top up?
Yes, in fact, that's the next thing I'm going to do. All right, so we could have done this one with algebra techniques, which is how you would have done this particular problem in Calc 1. So if we were doing this before, and I want to show you this not just because it's kind of cool, but because I want you to see it actually gives you the same solution. So if you were doing this in Calc 1, what you would have done is you would have actually factored the top. So how does x squared minus 2x minus 3 using algebra factor?
Plus 1 x minus 3.
Yes, it does. And then I am able to cancel the x plus 1s because they match. And I can find the limit as x approaches negative 1 of x minus 3, which is negative 4. Okay, so this should tell you, first of all, that they match. That's good. These two different methods gave me the same result. It should also tell you that if all I was doing was problems like these, I wouldn't need L'Hopital, correct? So there must be some other problems that we have that won't lend themselves to algebra to do them. Otherwise, we wouldn't need this. So let's take a look at another one, okay? Case in point. There's no factoring. There's no tricks that I can do that will handle this. Now, there is one thing I can do. I can use log rules on the top to write this a little bit differently before I do anything with limits. So how could I write this numerator so that it's easier to work with? 2 ln x. And it's much easier to work with a coefficient than an exponent. Derivatives are cleaner. I don't have inside-outside chain rule function kind of stuff going on. So this is easier to work with. So let's check then. What happens when I put the number 1 in on top? So what is the natural log of 1? It is 0. And of course, 2 times 0 is also 0. So this is 0 on top. And what if I put the number 1 in on bottom? I get 0. And while I could factor the denominator pretty quickly and easily, it doesn't help because I can't factor the numerator. Are you with me? Okay. So we are going to go then into L'Hopital's rule because I have an indeterminate form. I need to know what is the derivative of 2 ln x. It is. It's 2 over x. What is the derivative of x squared minus 1? 2x. And while you may be extremely tempted to simplify that algebraic expression, I contend that you don't need to, because you can plug the number 1 in and take care of the matter directly. Right? Yeah. So I plug the number 1 into 2 over x, I get 2 over 1. And if I plug this number in over here, I get over 2x over 2 times 1, which gives me, 2 over 2, which is 1. So this limit's 1. Easy peasy? Okay, we have one more. It's got a little trig, because it can't get too far away from trig. Okay. The other interesting thing on this particular problem is you've got an a and a b in here, and those are constants, but we don't have actual values for what those constants are. We're not given them. Now, we do need one condition as we're looking at this. Remember the original condition on being able to use L'Hopital's rule was, in fact, let me go back in here so I can say it, was that g of x does not equal 0, right? Except perhaps maybe at the particular point we're looking at, but the function itself can't be 0. And so in order to make this work, whoops, I cannot have this b value be 0. Because if the b value were 0, I'd get sine of 0 all the time, and the sine of 0 is 0. So b can't be 0. A could, and it would be okay, because it'd be okay to get a 0 in the numerator. That's actually not a problem, right? Yeah. All right, so my goal is to plug 0 in for x and to see what happens, because I don't have any simplifying like I did on the last problem that I need to do. So if I plug in 0 for x, what is the sine of a times 0? Well, I should say first, what is a times 0? 0. And then what's the sine of 0? 0. And of course, we can do the exact same thing on the denominator because it's the same thing except it has a b in there instead of an a in there. And this is an indeterminate form. It's 0 over 0, which means I can use L'Hopital's rule, right? It's good. Now I have the limit as x approaches 0. What is the derivative of sine of ax? Okay, so the derivative of sine is cosine of the same angle ax, and the derivative of ax is a. So we have a cosine ax. So then what's the derivative of sine bx?
B cosine bx.
B cosine bx. So far so good? All right, now we're going to try this again. We're going to plug in 0 for x and see what happens. So clearly, I've got the a. I'll come back to that at the beginning in a moment. But I've got cosine of a times 0. So a times 0 is 0. And then what's the cosine of 0? 1, right? It's 1. So this is actually a times 1. And then it's over what? B times 1, because it's the same function, just a different letter in there at the beginning, right? And, of course, when we multiply by 1, we just got a over b. So the trig was not any harder than the other ones, right? No. In fact, trig's really nice because things become zeros and ones very quickly and easily, which is nice to work with. One more, and this one has an interesting feature in it, which is why I bring it up. So this is an e to the x one now. So we've done something with logs, we did something with polynomials, we did something with trig function, now we're doing something with exponential functions, e's. So we're going to try plugging in infinity, which is a little weird to even say because infinity is not really a number. So you did this back in calculus, but let me remind you of how this works in case you haven't thought about it in a while, which is probably the case. The graph of x cubed looks like this, roughly speaking, right? If you're trying to find the limit of this as this goes to infinity in the x direction, that is, you're moving along the x direction, in the x direction infinitely, it means you're going along this curve and you're swooping up as you do, correct? That's what limits are. Limits are the value you're approaching. So if the x value is going right forever and you're tracing along the curve, moving in the right direction forever, what's happening to my y value? It's getting infinitely big as well. Everybody with me on that? So this is infinity on top. I realize infinity is not actually a number, but what we're doing on this side anyway, of course, is just giving ourselves a reference as to whether or not we're able to use L'Hopital's rule. We're not actually finding a number. Now, e to the x squared, it actually, e to the x, let me show you what e to the x looks like. E to the x looks like this. E to the x squared looks a little bit different, but it doesn't affect my value. It actually looks kind of like a parabola, but shifted up a little bit. Either one, no matter which one I drew, because you could interpret this from either perspective, has the same right-hand behavior. It goes up, just like the cubed graph did, correct? So if you're taking a look at this, we're still going right forever. What does it approach? What y value? Infinity, right? I'm getting infinitely large. That was how Cameron said it, which was perfect, actually. We're getting infinitely large as we move to the right. This is an indeterminate form, infinity over infinity. That was one of the forms that I was able to use L'Hopital's rule for, right? So then, what's the derivative of x cubed? 3x squared. And what's the derivative of e to the x squared? So the derivative of e to the power is e to the power. And then the derivative of this power, namely x squared, is 2x. Do not be tempted to just plug the value infinity into this. This is kind of like my natural log x squared problem number 2. I want to simplify before I have to plug anything in because it's going to make the problem easier to work with. What simplifies here? Yeah, this x and the square of that one, those reduce. So limit x goes to infinity. I have 3x over 2e to the x squared. But I have the 2e to the x squared, which its graph basically looks like the one I've already drawn on the bottom, right? I mean, it's a little bit more steep, but it doesn't have the different end behavior to it. I'm missing one graph. What does the graph of the numerator of this look like? Yeah, it looks something like this, right? It's just a diagonal line, right? And it's positive slope because it's 3x, and it is going to the right forever. So if I traced along this graph in the same way, moving right forever, I would also be moving up forever. So the limit, if I were trying to find a limit on this for 3x, would be what? It'd be infinity again. And I have already established that the denominator would be infinity, correct? Yeah. So now I've got the limit, and I'm going to be able to use L'Hopital's rule again. So this is the first example I did where you can use L'Hopital's rule more than once in a problem. It's perfectly fine. So if you try to plug the number in a second time and you still have 0 over 0 or infinity over infinity, you just get to use L'Hopital's rule again. So you could actually use L'Hopital's rule several times in a particular problem. This one's going to use it twice. All right, so what's the derivative of 3x? And once I get 3 here, it's pretty sure that I'm done with L'Hopital because 3 is a constant. It's just 3. There is no infinity left here. It's 3. What's the derivative of 2e to the x squared? Yeah, 2e to the x squared, actually, right? Okay. So again, the 2 stays, the e to the x squared stays, and the derivative of x squared is 2x. So 2x times the 2 that was already there is the 4x. Okay, so we said just a minute ago, I said just a minute ago, that this is a 3 on top. But again, what happens if I try to plug in infinity on bottom? It's still a large number approaching infinity, right? So what happens if I take the number, a number, that's a constant number, I don't even care what the number is, and I try to divide it by something that is infinitely large, and it gets bigger and bigger and bigger and bigger and bigger?
0.
That approaches 0, right? This is like the idea that if I took a cake and I divide it evenly among the 8 of us, we all get a pretty decent sized cake. If I take a cake and I try to divide it evenly among 100 students, all my students, nobody's going to get but a bite, right? And eventually, if I divide it enough, nobody gets anything. I don't know, you get a crumb or something like this, but eventually it comes down to you getting nothing. And that's what's going on here. This is 3 divided by something infinitely large. This limit is 0. So let me actually, let me pause this.